Hey guys, good afternoon. Today we are going to look at solving Legendre's differential equation. Let's continue. As you can see in slide 2, the Legendre differential equation has been stated there. You notice that the coefficient of the second derivative of y with respect to x is 1 minus x squared, and the coefficient of the first derivative of y with respect to x is negative 2x. Then the coefficient of y is n into brackets n plus 1. Let's continue. Now, since the Legendre differential equation has no singularity at x is equal to 0, we can solve it by a power series term expansion. We let y is equal to summation from 0 to infinity of as times xs. Now we get the first derivative of y with respect to x, which is given there, s times as x to the power s minus 1. We also get the second derivative of y with respect to x. We substitute all the above in the Legendre differential equation and we end up with an expression given there. Now, in the first term, we set s is equal to s plus 2 so that we get a uniform power of x to the power s in all the terms. Now, let's continue. Now, we get a final expression of s into s plus 2 times as plus 2 minus s into s minus 1 times as is equal to 0. Finally, we get a recurrence relationship of as plus 2 in terms of as in terms of n and s, which is given there in the slide. Let's continue. Now, from the recurrence relationship above, we can get a2 and other factors like f4 in terms of a0. We can also get the other terms of a3 and a5 in terms of a1. In other words, the recurrence relationship divides the expression into odd numbers and even numbers. So we get the final expression of y as a function of x equal to a0y1 plus a1y2, whereby the y1s are the even powers and the y2 are the odd powers of x. Let's continue. Now we finally get the Legendre polynomial Pnx to be equal to y as a function of x, which is given by a0y1 plus a1y2, just as we got above. Now you notice that the Legendre polynomial got is not a unique function because we have coefficients of a0, a0 and a1. Now to make it a unique solution, we can choose the coefficient of the highest power of xn to be an, and that coefficient an to be given by 2n Shrike over 2 to the power n times n Shrike squared. In other words, we've chosen the coefficient of the highest power to be given as an, like that. Let's continue. Now, since we know the coefficient of the highest power, the issue is to find the coefficients of the lower powers. But remember, we got from the recurrence relationship of as plus 2 in terms of as you can see in the slide. Let's continue. Now, we can express as in terms of as plus 2 as got from the equation above, and we get as a function of as plus 2 as given in the slide. Now, from the previous expression, we set s is equal to n minus 2, and this is what we get. We get an minus 2 is equal to n into brackets n minus 1 over 2 into brackets 2n minus 1 times n. But remember, we have an, the coefficient of the highest power, so we substitute there and we get an expression of the lower coefficients in terms of the higher coefficients, an, as shown in the slide. Thank you. Now we can go ahead and expand an minus 2. We expand the 2n Shrike factorial and finally get an expression for n minus 2. After getting the expression for n minus 2, we can get the expression for n minus 4 and other powers which are lower, like n minus 6 and n minus 4. Like in that slide, we've got n minus 4, which is also given there. Let's continue. Now, finally, we get from getting n minus 2 and n minus 4, we get a formula of the way n minus 2m evolves. We get a final expression of n minus 2m given by that. Now we go back and substitute in the general polynomial Pnx is equal to that coefficient times xn minus 2m. So we've got the expression for the general polynomial Pnx. Now you can go ahead and get P0x, P2x, P1x as shown in that slide. Thank you. That's all for today. Have a good day. Thank you for your time.